Hello students, today we start with the chapter The Binomial Theorem. Now this chapter is included in the IGCSE additional math syllabus. This chapter is included in the AS and A-level syllabus. This chapter is included in the IBDP, AA, SL and HL syllabus. So if you are from any of these streams, then I think you will be benefiting by watching this video, and today will be just the part 1 of this binomial theorem. We will be having a series of videos and they will be every Saturday from 7 p.m. onwards. So today is our very first session on this chapter, the binomial theorem, and of course anyone and everyone can join. If you are interested in knowing something new or else you want to revise your knowledge, then you can watch these sessions. Okay, so we start. What is the binomial theorem? As the binomial, this word binomial suggests, we will be having two terms, A and B, and they are connected by this plus sign. You can have a minus sign as well. Okay? And these two terms combinedly are raised to this power n. And for our today's session and for our future few sessions, at least this value, the value of n should be a positive integer. Will be a positive integer. Okay? So we are having two terms a plus b, and combinedly they are getting raised to the power of n. These are two variables a and b. They may be having any value. They may be pure numbers, 3 plus 5. But if you have two numbers, you just add them and take the sum total, raise it to the power of n. You don't do 3 plus 5 and to the power of n. What will be the expansion? We will be requiring some binomial theorem. No, 3 plus 5 raised to the power of 2. You will be just adding 3 plus 5 is equal to 8. 8 raised to the power of 2 is 64. Finished. But when you have one number as a variable and another number as a constant, suppose a is equal to 2 and b is equal to x. So 2 plus x, you cannot add them, raised to the power of 2. You cannot just add 2 and x, get a single term and raise it to the power of 2. That cannot be done. So you will be having an expression. What if we have a as 3x and b as x? Both are containing variables. A is 3x and b is x. Okay, let me write. A is equal to 3x and b is equal to x. Then what happens? A plus b will be 3x plus x, say raised to the power of 2. 3x plus 4x, these are like terms, even though they contain variables, but these two are like terms, so we can add them. 3x plus x will be equal to 4x whole raised to the power of 2 will be giving us the answer as 16x squared. Still, we do not require any binomial theorem. We do not know what type of a theorem is this. We have never learnt of this before. Okay, I am assuming that you do not know. Okay. So, if we have a value and b value, both are variables but both are like terms. Even then we can just add them to get a single term raised to whatever power is given, and we will be getting a single term as the final answer. But the problem arises when we have not the like terms but the unlike terms, dissimilar terms. They may have the same variable, they may have different variables. Like you may have, say, x square plus x cube. A is equal to x square and b is equal to x cube to the power of 2. But because these two are not like terms, we cannot add them to get a single term. We have to keep them as two terms. So we will be having the final expression will not be having a single term, it will be having multiple terms. So the problem arises when we have unlike terms. It may be one may be number, another may be variable, or both may be variables, but they may be two different variables, or they may be same variable raised to some power, different powers. So they are unlike terms. Whenever we have two unlike terms, then we need this binomial theorem. Then the necessity of this binomial theorem arises. Only then. Okay? Please excuse me, I'm not having a good voice today. My throat is giving some problem. Now coming to a plus b, it is a plus b. I have taken a plus b and I have taken different values of n. For the first case, n is equal to 1. As I have said, n will be a positive integer. So I have taken n to be equal to 1. A plus b raised to the power of 1 is equal to obviously a plus b. We are having two terms. When the power is 1, we are having two terms. This is important. We are having two terms in the final expression when the power is 1. When the power is 2, a plus b raised to the power of 2. This is a simple identity. So if you do not know this identity or you keep on forgetting this identity, you just multiply a plus b times a plus b. And I know that I think all of you know how to multiply binomials. You should be knowing because you have come to this chapter, the binomial theorem. So you should be familiar with multiplication of binomials or multiplication of polynomials. So I have just written the identity a plus b whole square equal to a square plus 2ab plus b square. Again I am saying you can do a plus b times a plus b and you will be getting these three terms after simplification. So over here the power is 2. N value is equal to 2, but the number of terms that we are getting is 3. When a plus b is raised to the power of 3, that means the n value is 3. You see the number of terms that we are getting is 4. That means always the number of terms that we will be getting in the final expression should be 1 more than the value of n. This is very important. Okay. The number of terms is equal to n plus 1. When n is equal to 1, the number is 2. Number of terms is equal to 2. When n is equal to 2, the number of terms is equal to 3 and so on. Okay. So the number of terms is equal to n plus 1. This is very important. What all are we seeing from this? First of all, let us expand this. A plus b whole to the power of 3. A plus b times a plus b raised to the power of 2. Because we do not know what is a plus b raised to the power of 3. So I am taking a plus b raised to the power of 2 and a plus b. I am multiplying them. So a plus b, in place of a plus b raised to the power of 2, I am writing a square plus 2ab plus b square. I have just substituted this part. Next we will be multiplying. A times a square is a to the power of 3 plus, and see, because there is this plus sign in between, we are having all positive terms. a times a square is a to the power of 3 plus a times 2ab is plus 2a square b plus a times b square is plus ab square. Okay. Plus b times a square is plus ba square plus b times 2ab is plus 2ab square and plus b times b square is plus b cube. And if we add the like terms, it is plus 2a square b and this one is ba square which is equal to a square b. So 2a square b plus a square b is 3a square b. And ab square and plus 2ab square is 3ab square. So we are having the final expression as a to the power of 3 plus 3a square b plus 3ab square plus b to the power of 3. Okay, there are 4 terms. Now, let us come to the a and b parts. What do we observe? For a plus b to the power of 1, we see that the first term is having a and the power of a is 1. Over here a plus b to the power of 2, the first term is again a and the power of a is 2. Whatever is the value of n, the first term is having only a and the power of a is the value of n. Over here a plus b to the power of 3, the first term is containing only a, that is over here. Whatever is written first will be coming over here. And it will be raised to the power of n. Doesn't matter what is the value of n, provided it is a positive integer. I am considering only the positive integers right now. So I am not going into the what all modifications will be done in case you don't have a positive integer power. I am not going into those details. Okay. So whatever is the value of n will be the power of a. This will be the first term. And now, but what is b? b is nowhere seen in the first term. We don't see b anywhere. A square, a to the power of 1, a to the power of 2, a to the power of 3. We do not see b. Why don't we see b? Because b is there but b is having a power of 0. Because anything raised to the power of 0 is 1, therefore the b part is not visible. b is there over here in this term, but b is having a power of 0. Also in this term, b is there, but b is having a power of 0. So for the first term, the first a is coming and it is having the power of n. And the second term is also coming, but it is not visible because it is having a power of 0. Now we come to the second term. For the second term over here, we are seeing only b, no a is visible. Why? Same logic, because you are having a to the power of 0 over here. So, b to the power of 1 and a to the power of 0. So, what is happening? You see the power of e is getting reduced from 1 to 0. It is getting reduced by 1. Whereas the power of b is getting increased by 1 from 0 to 1. So the power of the first term gets reduced by 1 and the power of the second term gets increased by 1. Okay. When we come to the second part, a plus b to the power of 2 whole raised to the power of 2, we are having 3 terms. The first term is a raised to the power of 2 and b is starting with a power of 0. Then the powers of a will be going on decreasing by 1 in steps of 1. So the middle term is having a to the power of 1 and the third term is having a to the power of 0. That is why it is not visible. What is happening to the b? b is starting with a 0 power, but its power is going on increasing in steps of 1. So the first term is having the power of b as 0, the second term is having the power of b as 1, The third term is having the power of b as 2. What about this? A plus b whole raised to the power of 3. Again, the first term a is getting raised to the power of 3 in the first term, and b is starting with the power of 0. And the a's powers are going on decreasing in steps of 1, and the b's power is going on increasing in steps of 1. So for the second term, a is having a power of 3 minus 1, which is 2. And for the third term, it is 2 minus 1, which is 1. For the fourth term, it is 1 minus 1, which is 0. Coming to the b, it is starting with the 0 power, and its power goes on increasing in steps of 1. So 0 plus 1 is 1. We are having b to the power of 1 in the second term. It is b to the power of 2. 1 plus 1 is 2 for the third term, and it is 2 plus 1 is 3. So it is b to the power of 3 for the fourth term. So now we see that there is a pattern. Okay, now we have understood that whatever is the value of n, we will be having n plus 1 number of terms. That we have realized, and we have also realized that all the terms will be, the a and b both will be present in every term, but the powers will be different. They may be the same in some of the terms or one of the terms, like over here a is having a power of 1 or b is having a power of 1. So, but the powers of the power of a will be going on decreasing in steps of 1, and the power of b will be going on increasing in steps of 1. So far clear? Now coming to the numerical coefficients, like over here we are having this 2, we are having this 3, this 3. Also we are having the ones. Let me take another color. There is this one over here. There is this one over here. This is 1, this is 1. This one is 1. This one is 1. So we are having a numerical coefficient for every term, and the numerical coefficient b may be equal to 1, may be some other number as well. So now comes the question, what will be the numerical coefficients? How to find them? For that, we take up the Pascal's triangle for the coefficients. Pascal's triangle. Just a moment, I have forgotten to open my calculator. Let me just open it. Yeah, sorry, it's coming on top. Okay, let it open and I'll be minimizing it. Pascal's triangle. It will be giving us the coefficients that are there, that are present in the final expressions or the expansions of the a plus b raised to the power of n. Okay, so we see that, okay, now it's clear. So we see in the first row, it is 1 plus 1 and 1. Let me just take this screen a little, this side. Okay. So the Damascus triangle, I'm starting over here. I do not know where am I appearing, so I have to keep some space over here. So a plus b to the power of 1, the coefficients are 1 and 1. There are only two terms. Therefore, I write 1 and 1. Okay. This corresponds to a plus b raised to the power of 1. This is the first row. When it is a plus b raised to the power of 2, we see it always starts with 1 and ends with 1. So we can safely write 1 over here and 1 over here. And there will be some number over here as well. How do I get that number? We will be adding these two ones. Okay, from the previous row, just above this place. 1 plus 1 is 2. So the second term's numerical coefficient is 2. This is the second row. And it corresponds to a plus b raised to the power of 2. Now comes the third row. Again we start with 1, end with 1. There will be 4 terms. So one will be over here and the other will be over here. We will be adding the two terms immediately above this position in the previous row. 1 plus 2 is 3 and 2 plus 1 is also equal to 3. So you see the two other coefficients are 3 and 3. And this corresponds to a plus b raised to the power of 3. Okay. So maybe now we are in a position to find what is a plus b raised to the power of 4. Of course, we can find a plus b raised to the power of 4 by multiplying a plus b with this final expansion of a plus b whole to the power of 3. We will be doing that just for checking purpose. Okay. But previous to that, let us find the terms of the final expression or expansion of a plus b to the power of 4. Using the knowledge that we have gained so far, we will be coming to the coefficients last of all. First of all, we are seeing the power is 4. In value is 4. Therefore, the number of terms will be equal to 4 plus 1, that is 5. Okay. And all the terms will be positive because there is the plus in between. And the first term will be starting with a to the power of the value of n, which is 4. Then I am not writing b to the power of 0 because it is equal to 1, so we do not write that explicitly. Next one, there will be some number, but the power of a will be getting reduced by 1 and the power of b will be getting increased by 1, that is b to the power of 1, plus there will be again some number. They may be 1, we do not know. We will be checking. We know this as 1 because the first coefficient is always equal to 1. We have seen that. Next it will be a square b square because the power of a is getting reduced and the power of b is getting increased by 1. The fourth term, a b to the power of 3 plus b to the power of 4. Again the coefficient of the last term is 1, so it is 1b to the power of 4 or simply b to the power of 4. The power of a will be equal to 0. So we will not be having any a part in the last term. So now we have to find out what are the values of these. What should we be writing in these three positions? Okay. So we need the fourth row. Let me just start from this a little before. Yeah. Fourth row, first value is 1, the last value is 1. There will be 3 more values in between. 1 plus 3 is 4. 3 plus 3 is 6 and 3 plus 1 is 4. So this corresponds to a plus b to the power of 4. Okay. Now we are in a position to write the coefficients. 1, then 4. Then 6 and finally 4. Okay. So the expansion of a plus b to the power of 4 is equal to a to the power of 4 plus 4 a cube b plus 6 a square b square plus 4ab cube plus b to the power of 4. Okay. So, okay. So now, let us check. We have got this expansion, but we are not sure because this is new to us, and how should we be sure? Someone has said that this is the Pascal's triangle and this way we get the coefficients. Why should we be trusting anyone? We have got the values 4, 6, 4 and I have just copied and I have just written them over here. But why should I be trusting? I know multiplication, so let me multiply and let me see that what do we get exactly actually. Do I get the same expression or not? Okay. So, I take a plus b to the power of 4 again. This is equal to a plus b times a plus b to the power of 3, which is equal to a plus b, and I am just copying this part. A cube plus 3a square b plus 3ab square plus b cube. Okay. So, now we multiply. A times a cube is a to the power of 4. A times 3a square b is 3a cube b plus a times 3ab square is 3a square b square plus a times b cube is ab cube plus b times a cube is, I am writing a first, so let me write a cube b plus b times 3a square b is 3a square b square plus b times 3ab square is 3ab to the power of 3 plus b times b to the power of 3 is b to the power of 4. Okay. Now the simplification part. We are done with the multiplication. A to the power of 4. Next term will be a to the power of 3 and b. So we see what are the terms that contain a to the power of 3b. This is 3. A to the power of 3b. Any other term? Yeah. A to the power of 3b. So plus 4a to the power of 3b. Okay. Next one will be a square b square. So this is one a square b square and this is another a square b square. 3 plus 3 is 6. 6a square b square. Then ab cube and ab cube plus 4ab cube and finally plus b to the power of 4. See, they match. So, we have verified that the Pascal's triangle can be relied. The Pascal's triangle give us the correct numerical coefficients. Okay. So, now that we have found a plus b to the power of 4 and of course you can find what will be a plus b to the power of 5's coefficient, you just go on getting the rows. I may write one of them, the a plus b to the power of 5, just for your practice. Again it will be starting with 1 and ending with 1, and 1 plus 4 will be 5, 4 plus 6 will be 10, 6 plus 4 will be 10 and 4 plus 1 will be 5. This is a plus b to the power of 5. Another thing that you may note is the symmetry. Each row is starting with 1, ending with 1, that is fine. But what about the middle numbers? When the power is an odd number, the number of terms is even. When the power is an even number, the number of terms is odd because it is n plus 1. When the number of terms is odd, you see, it starts with 1, increases to 2, and then again it comes to 1. When a plus b to the power of 4, it goes on increasing. 1, then 4, then 6. This is the largest number, highest number. Then it goes on decreasing. And this part is exactly similar to this part. It is just the mirror reflection. 1, 4, then the highest term, then 4, 1. Okay. Maybe you will be seeing this better, this symmetry. It will be more obvious to you if I take a plus b to the power of 6 as well. This is 6, 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6. See, a plus b raised to the power of 6, an even number. So the number of terms is odd. This is the highest number. It goes on increasing from 1, 6, 15. And then it goes on decreasing, 15, 6, 1. Now do you see the symmetry? And what happens if the power of n is odd? N is equal to some odd number. Over there you will be having even number of terms. This is having only 2 terms, so starts with 1 and ends with 1. What about the third row? Starting with 1, ending with 1. You see, because there are only 2 more numbers in between, both are the same. 3 and 3. For a plus b to the power of 5, it is starting with 1, ending with 1. In this case, you are having 2 middle terms which have the highest values as the same. There will be 2 terms containing the same coefficient when the power is an odd number. When n is an odd number, you will be having 2 terms having the same numerical coefficient. Like when n equal to 3, when n equal to 5, you are having 2 terms containing the same coefficient. Of course, you will be having, these also will be having the same coefficient, but these two will be the 2 adjacent terms. And the coefficients will be the numbers will be the highest numbers. Okay. So this is the symmetry that you have to realize. Clear? Another thing that should be coming to your mind is, okay, so you have shown us so many things, but they are all with plus sign. They are all with plus sign in between. Plus sign in between. How does it change, or does it at all change when we have, if we have instead of a plus b, we have a minus b? Let us see. For a minus b raised to the power of 1, it is simple a minus b. So you see there are 2 terms. Previously you were having 2 terms, even now you are having 2 terms. Previously the first term was starting with a, even now the first term is starting with a. The power is equal to, power of a is equal to the value of n. The b's power is starting with 0, that's why it is not visible in the first term. Next, the power of a goes on decreasing in steps of 1 and the b's power goes on increasing in steps of 1. So the second term is having b to the power of 1 and the a's power is 0. Clear? But what about a minus b raised to the power of 2? For this I am not multiplying, I am using the identity. You can multiply a minus b times a minus b and you will be seeing that you get this expansion. A to the power of 2 minus 2ab plus b square. So previously there were 3 terms, even now there are 3 terms. The first term is having the power of 2, the power of a is going on decreasing in steps of 1, the power of b is going on increasing in steps of 1. Everything is the same. This is a square plus 2ab plus b square for this, and this is a square minus 2ab plus b square for a minus b raised to the power of 2, whole raised to the power of 2. What is different? The difference is, in this case it is plus 2ab and in this case it is minus 2ab. Sorry, it is minus 2ab. Okay. This is of course the plus a square. Always it is starting with a plus sign. Over here also it was a plus b and now it is a minus b. Starting with a plus sign, then the second term is having a minus sign. What about a plus b raised to the power of 3? Whole raised to the power of 3. It will be, this is we have got. So let us get a minus b whole raised to the power of 3. A minus b whole raised to the power of 3 will be equal to a minus b times a minus b whole square equal to a minus b and a square minus 2ab plus b square from this part I have taken. Okay. And now I'll be doing the multiplication. It is a times a square is a cube. A times minus 2ab is minus 2a square b. A times b square is plus ab square. Minus b times a square is minus a square b. I am writing a first. You may write minus ba square also, doesn't matter. Minus b times minus 2ab is plus 2ab square. And minus b times plus b square is minus b cube. So this is equal to a to the power of a to the power of 3 minus 2a square b and minus a square b is minus 3a square b plus ab square and plus 2ab square is plus 3ab square and minus b cube. So you see the difference. This is a cube plus 3a square b plus 3ab square plus b cube. And this one is a cube minus 3a square b plus 3ab square minus b cube. So it starts with a plus sign. But then the signs go on alternating. Plus minus, always the signs will be alternating. This is the only difference between a plus b raised to the power of n and a minus b raised to the power of n. So, if you have this a plus b raised to the power of 4, we have got the expansion by both the ways using the Pascal's triangle and by multiplication. Now, if you have to get a minus b raised to the power of 4, I am not going into the multiplication process anymore. Just you go on alternating the signs. The first sign will be a plus. Then minus 4a to the power of 3b plus 6a square b square minus 4ab cube plus b to the power of 4. Okay. This is the only change that you will be having. For a plus b raised to the power of n, every term will be a positive term. For a minus b raised to the power of n, the signs will be alternating. It will be starting with a plus and then plus, minus, it will be just continuing. Okay? This is the only difference. And so we now understand that we can get the numerical coefficients using the Pascal's triangle, and it is also very easy. We do not have to do any complicated calculation. We have to just add the numbers. But suppose you are asked to get a plus b, let me write over here, a plus b raised to the power of 20, and you have to get the final expression. You know the number of terms you will be having in the final expression will be 20 plus 1, which is 21. First term will be a to the power of 20, last term will be b to the power of 20, even that we know. But what about the numerical coefficients of the middle terms? The remaining 19 terms. We do not know them. And if we have to use the Pascal's triangle, of course we can use the Pascal's triangle. But you can very well understand how many rows do we have to calculate in order to come to this a plus b raised to the power of 20? It will be the 20th row. We have to calculate all the 19 rows, though we do not require any of them. But in order to get the coefficients of the 20th row, we need all the 19 rows. That is why, even though the Pascal's triangle is so very easy to use, we do not use it very frequently. Because if the power or the value of n is a large number, then you have to do so much of calculation, although simple calculation, but it will be taking a long time. It is a laborious calculation. Not difficult, but laborious, time consuming. Time consuming, space consuming, energy consuming, so we do not use this method. So, how to get the coefficients? For getting the coefficients, you have to remember one thing, that, what did I say? This is the first term, this is the first term, this is the second term. But no, you cannot, this is the usual way of calculation, right? But we do not consider them to be first term and second term. Rather, we consider them as the 0th term and the first term. We always start with the number 0. So this will be the 0th term, this will be the first term, and this will be the second term. Over here, this is the 0th term, this is the first term, this is the second term, and this is the third term. Okay? So now you see the third term matches with this number 3 because we are starting with 0. But when you have to remember that the total number of terms will be equal to n plus 1. Don't get confused. If you just start your counting with 0, then the last term will be the third term, of course. But the total number of terms is, of course, equal to 4. Okay, 1, 2, 3, 4. There is no doubt about that. Okay. For this also, a plus b to the power of 4. This is the 0th term, this is the first term, this is the second term, this is the third term, and this is the fourth term. Okay. This you have to remember that it will be starting with 0 and not 1. We are actually habituated in calling this as the first term, but for binomial theorem we will be starting our counting with the number 0. Okay. So this is the 0th term, the first term, and so on. So let us go to this part. We have two coefficients for this and this, and n value is equal to 1. We have something called NCR. This is also written as, you can use this notation or this notation. This is, you read it as NCR. It is a combination. Don't have to go into combination details. The SL people, IB Maths SL people, you don't even have the permutation combination. So don't have to bother yourself with what is C and all. NCR, you can write it in this form or you can write it in this form. Both are valid. Okay. You can get the coefficients, the numerical coefficients of the final expansion of any binomial expression, a plus b raised to the power of n, using this NCR technique. N is 1. Okay. So for the first term is starting with 0. So R will be 0. 1C0. What is this equal to? Let us find using the calculator. Okay. So this is the TI Nspire calculator, and I am going to menu, and it is the calculator, add calculator, menu, probability combinations, NCR, you see, 1 and comma 0. Enter. Say it is 1. For the next term, so it is 1. We are having the numerical coefficient as 1. What about this? This is the first term. So it is, n value is the same. N is 1. It is 1C1. What is this value equal to? Again, going to menu, probability combination 1, comma 1. Enter. Again 1. Hence, we are having 2 ones. Okay. Coming to a plus b raised to the power whole raised to the power of 2. I am not going into these ones because we have seen that always it starts with 1 and ends with 1. But what about the middle term? For this, the n value is 2, so it will be 2c. And what is this? This is 0, 0th term. This is the first term. So it will be 2c1. Let us see what is the value. So menu, probability combination 2c1. See, it is 2. Okay. Coming to a plus b whole raised to the power of 3. I am not going into these will be 3c0 and 3c3. So, and you can try it, they will be equal to 1. Coming to this one. It is 3c1. What is this equal to? Menu, probability combination 3, comma 1. See 3. And let me do 3c2 as well. Probability combination 3, comma 2, 3. So you are getting 3 as the numerical coefficients for both the terms, both the middle terms. Okay. So this is 3 and this is also 3. Hence we are getting these two 3's over here. So you see, you can avoid the Pascal's triangle because you have to avoid. You don't have any other alternative. When n is a large number, you have to avoid. Okay. Coming to a plus b to the power of 4. What happens? Let us see. 4c0 we know. So we start with 4c1. 4c1 is 4, comma 1, 4. So it is 4. See, this is 4. 1 is that this is the 0th term. So this is 1. This is 2. This is 3. And this is 4. Okay. Coming to 4c2. What will this be equal to? Menu, probability, combination 4, comma 2. Enter. See, 6. 6. And in fact, you can get, okay, let me show you. 4c3. Let me compute 4c3. So it is a menu, probability, combination 4, comma 3, enter, 4. Okay. But you really do not need this one because you know the symmetry. A plus b raised to the power of 4, hence there will be 5 terms. So this is the highest number. You have come to the highest number, reach the highest number. This is the middle point. So now the coefficients will be going on decreasing. So this is 4 and this is finally 1. Okay. If we just want to verify this one, see this one is for 0, the first term, this is for the second term, this is for the third term, this is for the fourth term. So the n value is 6. It will be 6C4. Let us see if we get the number 20. Menu, probability, combination 6, 4. Enter. Sorry, it is 15. What do I do? Oh, sorry. My bad. It is 1, 2, and then 3. Right. That is why you are getting 6C4. Okay, let us see what is 6C4. It is 15. They have given 6C4 as 15. What is 6C3? This should be 20. Menu, probability, combination 6, 3. See, it is 20. Okay. So this way you can get the coefficients of the binomial expansion terms and you can avoid using the Pascal's triangle. Okay. So let us stop over here for today. This was all for this session. And if you have any queries, any confusion, please feel free to write to me in the comment area. I'll be trying to help you as much as possible. Thank you for staying with me. Bye.